Welcome to Starting with DuckDB and Python. My name is Christopher, and I will be your guide. This course is all about DuckDB, a popular open-source database. Along the way, you'll be learning about how to use DuckDB as an in-memory database through Python, using it as a more traditional file-based database, and just enough SQL to get you going, along with how to incorporate Python functions into your DuckDB calculations. DuckDB is a third-party library. As always, best practice is to use a virtual environment to do this. Do pip install DuckDB or whatever tool you like to use to do such things. The code in this course was tested with DuckDB version 1.2.2 and Python 3.13.3. I'm not using anything 3.13 specific though, so older supported versions of Python should be fine. DuckDB, I promise I won't do that every time, is an open-source database. It's column-oriented, which means it shares some aspects with data frame libraries like pandas and polars. In fact, it has built-in calls to integrate with both those libraries. And although it is a relational database, its focus is a little different than your typical Postgres or SQL server. It isn't meant to be a shared backend on a server, but a tool for doing data analytics. If you use a data frame library and sometimes wish you could just use SQL to solve a problem, then DuckDB, seriously, ignore me, I'll get bored and stop eventually, might be the solution for you. The database, whose name I will now skip, can be used directly like SQLite or through a programming language. And that's pretty much any language you want, as it integrates with over 20 of them. They divide the support into 3 tiers, and how quickly features and fixes get applied depends on the tier. Python is one of the 10 primary support tier languages. One result of the data analytics focus is that both in-memory and traditional file-based database operations are supported. Another result of that focus is the integration with a wide variety of data formats. In this course, I'll be using CSV, JSON, and Parquet. Before diving into DuckDB, I behaved myself that time, you need to know a bit of SQL. This isn't a SQL course, and the only stuff I'll be using in practice is the select statement. You can probably get along with just reading what's on the screen. But in case you need a refresher, I'll give you a quick intro next. If you're comfortable with basic SQL, feel free to skip to lesson 3. In the previous lesson, I gave an overview of the course. In this lesson, I'll give a quick overview of the SQL language used by relational databases. SQL is short for Structured Query Language and sometimes gets pronounced SQL and sometimes SQL. I'm inconsistent myself, so if one or the other bothers you, I'll likely annoy you one way or the other in this course. It's a domain-specific language for relational databases. It's quite in-depth, but you can get fairly far with just some basics. The create, read, update, and delete, that's CRUD, operations are used to manipulate data in the database, or can be used to manipulate the database itself, like managing tables and rules, etc. SQL is a declarative language. That makes it a little different from Python, which is mostly a procedural language. Instead of specifying the steps you want of an operation, you declare the result you're looking for, and the execution of that statement produces your desired outcome. With simpler statements, this is kind of an academic thing. With more complex statements, it can get a little hairy. SQL has a lot of dialects. The basic stuff I'll be using in this course will work in pretty much every database out there, but more advanced SQL tends to have flavors, and you need to be careful. Just because you know how to talk to SQLite doesn't mean that Oracle will listen to you that exact same way. The fundamental unit of a relational database is a table. A table is like a spreadsheet consisting of rows and columns of data. Unlike your spreadsheet, each column in a database table has a data type. If you try to put the wrong kind of thing in a column, you'll get an error. That's actually a good thing. It prevents some of the sloppiness you can encounter in a spreadsheet. A database can contain more than one table, and the actions you perform can affect multiple tables. There are 4 basic operations that are common to all dialects of SQL. These are the CRUD operations for the data in a database. Select is for reading data, insert is for creating data, update is for updating, and delete is for solving complex mathematical problems. Or deleting data, I can't remember which. As I mentioned in the overview, I'm going to stick with select for the purpose of this course, so I'll show you a few variations on it to get us going. Consider the table on the screen here. It's named Actors and has 3 columns. The first and last name columns contain strings, while the age column contains a number. Different databases have different ways of storing strings, and most of them don't call it a string, but I'll stick with that terminology for now. The Actors table currently has 3 rows, specifying 3 different actors. Inside of a database shell or in a program, you could execute a select statement to read rows from the database. The select command needs 2 things: the name of the table to read from and the name of those columns you wish to get data out of. Let me show you an example. It's common practice in SQL to capitalize the keywords, although in most databases this isn't necessary. Our statement here has 2 keywords: select to tell the database I want to read something, and the from keyword that specifies which table I want to read that something from. The last name and age values are the names of the columns that I want the query to return. The end result is 3 rows of data corresponding to the 3 rows in the database table. Depending on the tool you're using, the result can be formatted in different ways. Most command line database REPLs show comma-separated values. They may or may not show the column names that go with this. In some databases, it's an option you can turn on to control the result. If you were going to do the same thing in a programming language, the database API would return the result in some sort of object format, possibly a tuple of tuples or something more complex like an iterable. When selecting data from a table, it's quite common to want all the columns. To save you typing, SQL has a shortcut. You can use the star character in place of the column names. Let me show you what that looks like. Same table as before, but this time, because I used the wildcard, the result contains all 3 columns from the table. Most of the time, you only want specific rows, not everything out of a table. You constrain which rows you want using the where clause. A where clause specifies a comparison operation similar to an if statement. Only rows that meet the criteria in the where get returned in the results. Here's an example. Note that you're still specifying the columns and table for the select, but this time you're adding a where component. The criteria for this where says any row where the age is greater than 50 should be returned. Note in all 3 examples so far that the SQL statement has ended in a semicolon. Some databases don't care about this, and will figure it out if you leave it off, but most can be finicky about it. It's best practice to remember it. You can mumble under your breath throughout the rest of this course as I ignore best practice because DuckDB doesn't care. I'll only be using the select statement in this course, but I'd be remiss if I didn't show you the CUD part of CRUD. See how well behaved I am? I could have stuck a cow sound effect after that last bit. An insert statement creates a new row in a table. Like with select, you have to specify what table you're inserting into. This statement takes 3 keywords: insert, into, and values. Insert into always gets used together. You see, the folks who invented SQL wanted to make it read like a natural language. I kid you not, they thought that non-programmers would use this stuff. In a later lesson, when I show you a table join, you'll understand why that's funny. Within the insert statement, after the table name, you specify what columns your new data will be going into. This might seem like overkill because the order of columns in the table are specific, but some columns support default values, so you could insert without specifying everything. After the values keyword is another grouping. This one contains the actual data. I haven't done it here, but there are ways of inserting multiple rows at a time as well. To change an existing row in the database, you use the update statement. This statement also has 3 keywords in it. Like with other statements, you specify what table you're updating first, and then the set keyword specifies what change you'll be making. In this case, it's the spelling of Skarsgård, with the correct accent over the A. Then, like with a select, you use a where clause to specify which rows get updated. Most of the time this is a single row, but it doesn't have to be. If there were multiple Skarsgårds in our database, all of them would be affected by this statement. And finally, the D in CRUD is for delete. Delete from is like insert into, and the where clause specifies the criteria used to determine which rows to delete. Like with the update example, if there were multiple lunas, they'd all be removed. Most of the time, your table will have a sequence column. Think of it like a counter that's automatically updated by the database. This gives each row a unique ID, making the update and delete clauses easier to write, as the where can specify the ID of a single row if that's what you intend. Next up, what you came here for. Let the duck puns begin. In the previous lesson, I gave a quick refresher on SQL. This lesson is your first foray into DuckDB. Quack. I was too lazy to edit the sound effect in that time. DuckDB is a little different from your usual database in that it happily works on table-like things in memory, as well as in your more traditional file format. This means you can load data into memory similar to how you would with a data frame in pandas or polars, and then perform operations directly upon it. Once you're happy with it, you can optionally send it down to a file database for future use. The key interface to this mechanism in the Python API is an object called DuckDB PyRelation. It's a bit of an ugly name, but you'll never have to type it out. You'll be getting these objects back in return from calls to the API. The methods on DuckDB PyRelation are very similar to those on a data frame, meaning you can inspect the data, get information about it, and perform calculations. If you're not familiar with pandas or polars and haven't played with data frames before, don't worry about it. I'll walk you through the operations. DuckDB interacts with a variety of file formats, including CSV, JSON, Parquet, and much more. Some of these can be ingested through read methods in the library, while others are available through plugins. Let's waddle over to the REPL and take a quack at the API. Yeah, I know that's bad. It's only going to get worse from here. Okay, let's dive in. I use that expression all the time, but this time it comes with the extra visualization of a duck dipping below the surface. As you might guess, the first step is to import the library. The module defines several functions you can use, including one to directly call SQL. This select statement's a little different from the ones I showed you in the previous lesson. It is dynamically generating a result without querying any tables. You'll almost never do this in practice. Just consider this a hello world-like query that doesn't require any tables to work. You're unlikely to do much with SQL unless you actually have data. So let's get some data. The data files I'll be using throughout this course are available in the supporting material dropdown below the video window. Parquet is an open-source column-based data format from the Apache project. Parquet includes data type information and supports compression, so it's become quite popular in the data science world. Let's look at the result. There you go, 47 rows of American presidents. Let me scroll back up here a bit. At the top of the output, you can see the names of the columns and their data types. Like with the actors example in the previous lesson, you've got first and last name information. The result here also contains a sequence number. If you're coming from other databases, consider this a primary key. If you're coming from pandas, this is an index. Either way, it helps you uniquely identify a row. I'll just duck back down here. They'll keep coming. I can't be stopped. Now let's examine the result object. The shape property is a tuple telling you how much data you have. The first element is the number of rows, while the second is the number of columns. If you've used data frames before, this should be familiar to you. The column information I showed at the top of the table output is also contained in a property. The columns property has the names, while the dtypes property has the data types. Like with a data frame, there are a variety of methods available that let you explore the contents of the object. Count counts the number of items in a named column. In this case, the same result would have happened regardless of what column I chose, as there are 47 rows. Describe gives an overview of the contents, column by column. Note at the bottom here that it says there are 7 columns, but 5 are shown. This is because the result is too wide for my screen. Each row in the result contains a different statistical operation for each of the corresponding columns. You already saw count. Well, mean, standard deviation, min, max, and median perform those calcs for each column. For some operations, that doesn't make sense. You'll never need the standard deviation of the sequence column, and you can't do a standard deviation on dates, but the info's there for everything. The first method returns the named column's value for the first row, while the histogram method gives a histogram of the data, counting the number of instances of each item in the named column. Note that the result of each of these operations has been a summary table, very similar to when I printed out the president's object itself. That's because both situations return a relation object. For now, I'm showing the evaluation response of a relation object. Later, I'll show you how to access these programmatically, which is one way to get at those two columns that got truncated off of the screen. If you don't feel like typing SQL, DuckDB provides methods that follow the same logic. For example, you can select. Let me scroll back. Like with an SQL select, I gave the column names to be selected. The table part is implicit here as the operation is running on our object. Also, like calling select as SQL, the result of this function is a relation object, in this case containing the last and first names from our data. I'll scroll back down. There are other query-like operations as well. Unique removes duplicates. Notice there are 40 rows in that result, so 7 presidents have duplicate last names. Some of those are relatives, and some of those are because of gaps between terms. The results from the describe call can also be queried on a column directly. Max returns the biggest value, which for strings is the alphabetically last result. Min is the smallest, and sum is the total. Summing the party ID makes no sense whatsoever, but it was an integer and I wanted to show it. Crazy, I know. You might even call me quackers. Mean, the average of the party ID, is just as silly, but like I said, integers for the demonstration win. What did the duck buying lipstick tell the cosmetician? Put it on my bill. Next up, I'll move from in-memory operations to file-based ones. That and more duck puns. It'll be foul. In the previous lesson, I started your DuckDB journey by showing you the relation object. In this lesson, you'll get to do more database-y things and put your SQL knowledge to practice. Okay, let's do some typical database-y-like things. To interact with DuckDB's file-based mechanism, you need a connection. This is pretty much the same as any database API, and like other file-based databases, the connection takes a file name as an argument. The resulting connection object then is your API access point for your operations. In the previous lesson, you saw how to get a relation object using the read parquet call. If you've got data like that and you want it in an actual database table, you can do that using the toTable method. Off to the REPL. I promise I'll go easy on the duck puns. I wouldn't want you to think I was mallard-justed. Like before, I start out by importing the duck. This time, I'll also need a connection. In the supporting material drop-down below the video window, you'll find sample code. Inside that, there's a directory called data, which includes the files that I'm going to load. So I don't confuse files I produce with the files that I've loaded, I'm putting our output database in a directory called processed. If you're coding along with me, you'll need to create that directory before running the following command. When you connect using the database argument, DuckDB either loads an existing file or creates it as necessary. All subsequent operations on the connection I've just created will be on this newly created database. Since it is new, it's empty. Let's get some data. This is the same call as in the previous lesson, where I've loaded the president's parquet data. I've intentionally used a rather long name for the results here to distinguish between the relation object and the things in the database. In the real world, you probably wouldn't bother with this, but I'm hoping to keep it clear when something is in memory and when something is in the table, at least for now. DuckDB's power is the ability to go back and forth between memory and file. This can also be a little confusing. Several times when I was writing the sample code, I failed to write something to the database because I was in memory and I thought I was in a table. It's just something to keep in mind. Confusing or not, it's powerful. Let's put some of that SQL to practice. I'm going to select the sequence last name and first name columns. Selecting from the relation object. See, that's cool. Even though I'm in memory, I can still do databasey things. And rather than look at all 47 rows, I'm going to restrict it down to a small sequence number. And the result is the first two precedents. Now remember, the precedence relation object is an object. It isn't in the database yet. To put it there, you use the toTable call. This method has created a table named precedence in the database containing all the same stuff from the relation object. When you're done with a connection, you should close it, especially if you're writing long-running code. Connections take up memory, and you should tidy up after yourself. If I were more clever, I'd put a pun about feather dusters in here. To prove that the content got put into the database, let's connect to it again. Same call as before. And some similar SQL. Note the difference. This time I'm selecting from the precedence table, not the relation. Since the relation got converted into a table, you shouldn't be surprised to see the same data. I do have something that might be a surprise, though. Close your eyes for a second. No peeking. Get it? Like the roast? I'm sure you want to roast me at this point. Of course, you can't really pay attention with your eyes closed, so here it goes. And falls down. This call queried the relation object, not the table. Since the relation object was created using the original connection, it can't be used with this new connection. Relation objects are specific to the connection. Don't close your connection too early if you still need to perform operations in memory. So far, I've only used the Parquet format. To be productive, seriously, no power in the verse can stop me, you may need to work with other formats. In the next lesson, I'll show you CSV and why it can occasionally be challenging.